We'll get started. Is everyone having a good first week? Yes? Okay. Um, you have seen my website by now, and I have also posted the first assignment, which is posted here. And I got a few questions from students. For example, the video recording talked about a different aerofoil, maybe even different format of the report and so forth. Remember that this was recorded almost a year ago for a different class, so I was teaching it as part of that class. Okay, so your assignment is going to be obviously going to be for aerofoil specified in the assignment, and there are specific things that we are going to look for. For example, we are going to look for a graph of CL versus CD. We are going to define what all of these mean in a minute, and we are going to look, the grader will look for that particular plot, okay? And then he or she will also look for the tabulated data, just in case plot is wrong. And then the data will be provided as an Excel sheet, okay? And then you should plot the CP versus X over C for the three aerofoils at a fixed lift coefficient of 0.5, in X foil. You can specify alpha or you can specify the CL, okay? So I would like you to watch the video on X-Foil. There are also lots of tutorials, get started on it. I won't be going over it here, but this is like a prerequisite. And comment on how the pressure distribution, behaves and how it affects the transition. I'll also be addressing it in the class. Today is already Wednesday, a little bit today, and then also on next Wednesday. Monday is a holiday, okay? All right. Any questions on this? Anyone has any comments or questions you want to ask on the homework? Yes, sir.
The x-axis, that's not normally how a drag polar is.
It's drawn both ways. For example, we will show you a report by Abbott and Deinhoff. NACA a long time ago for 2D aerofoil, they used to put alpha on the x-axis or CL, CD on the y-axis, so it looked like a parabola. But in some vehicle performance classes, they would have rotated it so that the C capital D is on the x-axis, C capital L is on the y-axis. But for this assignment, please plot it the way I have asked it to do. Okay? Good question. Great question. Yeah. Also, you should comment on why the three different drag polars differ. They will differ because of the drag. On an aerofoil, as we will see, the drag could be based on skin friction, which is the boundary layer scraping past the surface. So if you have a laminar boundary layer, it's got a less drag compared to turbulent boundary layer. So the more laminar flow you have, the more lower the drag. Okay, that's why one aerofoil will behave better than the other. Okay, again, I'm going to be covering some of it in the lecture here. How the laminar flow to turbulent flow change is called a transition. X-foil will predict where the transition is taking place on the upper surface and also on the lower surface. So you can watch it. So it'll clearly tell for certain aerofoils, like 4-digit aerofoils, transition takes place a lot more quickly. But for turbulent flow, for the 5-digit and 6-digit aerofoil, it takes place much later. Why does it happen? Because if you look up a boundary layer on an aerofoil surface, these molecules are moving from left to right, okay? And they are subjected to two different effects. One of them is the viscosity at the wall. Wall is not moving, so it pulls everything back towards you. Like as you're running it, if you step on a chewing gum, your head wants to move, your feet wants to stay put, okay? So that you get this gradient. So you're being slowed down steadily, as you go from left to right. So molecules slow down, boundary layer gets thicker and thicker and thicker. You may have seen this in your undergraduate studies. But on top of it, you have something called the pressure gradient, okay? Pressure gradient is when the pressure is changing from upstream to downstream along the surface. So if the pressure is rising, it's called an adverse pressure gradient, okay? If the pressure is dropping, it's called a favorable pressure gradient. So when you're running as a runner, if you have a high pressure behind you compared to in front of you, it pushes you, it helps you keep moving. On the other hand, if you have a high pressure in front of you compared to behind you, it's also slowing you down. So these two combined effects, adverse pressure gradient, which means pressure is rising as you go from left to right, delta P over, let's say call this distance surface distance equal to S, is greater than 0, then the boundary layer at some point becomes like this S-shaped curve. Sometimes it may even fully reverse. This is what causes the stall. Flow start flowing backwards. We have a video called Stall. I would like you to watch it because, again, it's a prerequisite material. There they will show you animated how the stall occurs. Okay, but this S-shaped here, a boundary layer, has got a convex, concave. If you notice the curvature, if you draw it sideways, it'll go like this, then it'll go like this, convex, concave. So when the curvature changes from convex to concave, it's got an inflection point where it switches from convex to concave. Okay, so somewhere along the way, the first derivative stopped at dropping, then it started rising. Okay, that's what happened. Okay, so there's a British scientist called Rayleigh, Lord Rayleigh. He said if the boundary layer has got an inflection point, it's prone to become turbulent. Okay, it'll become quickly turbulent. So the adverse pressure gradient on the surface, which is we are going to plot by a quantity called Cp, which I will define it in the lecture today. Although it's a prereq, it's an important concept. So when the pressure gradient changes adverse too quickly, then it's going to become turbulent too quickly, then the drag is going to be higher. Okay, so this is how you will determine the behavior of the drag polar. Okay. Today's lecture, everything will be recorded. If something is not clear, you can always review it. You can ask me questions in the class. Okay, until the day before the exact homework is due. Right after that, it's kind of you can still ask me, but it won't materially influence your grade on the homework. Okay. Second thing you need to also notice, some questions students had a formatting, how do I format it? There's no particular formatting instructions given here. My video had some formatting instructions for last year, but as long as you have these few things, my grader will give you the full grade. But it's always nice to have a nice cover sheet saying your name as AE6015, assignment number 1. And then put the report format with a nice labeling of different sections. Maybe a section says a drag polar of the three airfoils. Draw the plot. When you draw a plot, give it a label or a title. Figure 1, drag polar of the 3 airfoils. Okay, it just makes it more visually appealing, and also it makes it more easy for you a year from now to see what's happening, rather than just to have a bunch of stuff on a piece of paper. Okay, and you may also want to have some references. At least you're going to be using X-file. Okay, so you may want to reference X-file, and maybe you want to reference the class notes if you want to. It's up to you. Reference could be EndNote or the footnote. Okay, either way is okay. Again, it just tells you a year from now where did this data come from. And it just has a nice visual appearance. Okay, so graduates, recruiters, look for good written examples, samples. Of course, you'll be doing research with your professors, publishing papers. Those things add your value to it. But this is a good way to document the work you do. But my grader primarily will focus on the content, but I encourage you to have a nice visually appealing format, just for your convenience. All right? Any questions on these? Are you all okay with it? Yes, please.
Whenever we're varying the CL, what kind of increment are you looking for?
Okay, very good question. Maybe, for example, 0.1 is sufficient, minus 0.7 to plus 0.7, it'll give you 15 points. So it'll give you a nice either parabola shape or something unusual. Okay. If you have time, you can do more, but it's okay. But when you tabulate it, your table will have X file, by the way, will plot alpha, CL, CD. I'm going to define all these things in today's lecture. Something called the pitching moment. Then it will also plot where did the transition occur on the upper surface, where did the transition appear on the lower surface. So you may want to capture that as an Excel sheet. So you have the data table on an Excel sheet. Okay. By the way, some people ask, can I use, instead of a MATLAB, Python to draw the plot? That's fine. Any tool you want to draw the plot is fine. Okay. I just use MATLAB because I'm brain dead. That's pretty much Fortran and MATLAB is what I usually use. Although I can understand a little bit of Python. Great question. Anything else? Are you all okay with this? So last lecture, let's list the concepts that we studied, and let's see the various things which we studied. We studied concept of continuum. There were two things we had to study. One of them is called the mean free path. Could somebody tell me what is the mean free path? We gave it a symbol lambda. What does the mean free path mean in your mind? Yes, please.
The average distance molecules have to travel to collide.
Before they collide with each other. Great, yeah. So in this class, for example, it's very sparsely populated, so it's about half a meter some places, at least 1 foot in other places. I mentioned, in delta flight, it'll be more like a micrometer, things like that. So, but anyway, molecules in our room here are very closely packed. So when they travel, they're going to travel as a group, okay? So the average velocity is what we measure with a pitot probe or a velocimeter in a lab. You can visually see it. Cloud moves from left to right. You see the whole pattern moving. So what it is an average property over thousands of, really billions of molecules, trillions of molecules. On top of it, they have a random motion to it. Some molecules are going this way, some molecules are going that way. The analogy I would sometimes use is in a baseball game, at the beginning of the game, people will be coming in, but some people will be going to go get a drink or get a soda or a hot dog. So you'll see this milling motion, but in an average sense, the bulk of the people will be moving in, and then they'll be going to their seats. That's the average velocity is going inwards, but on top of it, there's a random motion to it. Likewise, towards the end of the game, most of the people will be going out, but some people will still be, milling about. So there's a random motion. So mean free path tells you the distance molecules travel before they bump into it. So because they bump into it, the group velocity or the average velocity of one particle is not going to be dramatically different from the other one. So we can just use a single velocity for that bunch of particles. So this is what we call the concept of continuum. And then we used something called the Knudsen number, which is the ratio of a lambda divided by L, where L is the vehicle dimension. Could be a fuselage length, could be a span of the wing, any convenient length. As long as this lambda is much smaller than L, then we can use a concept of continuum. You can assume that everything is traveling together, right? The second concept we talked about was the properties of the fluids, density. Could somebody tell me what is the units we will use for the density? What are the convenient units in the international system of units? How would you measure the density? It's a mass per unit volume. what's the mass you would use in the International System of Units? You're smiling, so you know the answer, okay? Yeah, okay, all right. Kilogram mass, okay? Yeah, and the volume is meter cubed, okay? How about the British System of Units? Pardon me? Yeah, speak up. Okay. Slug per cubic feet, okay. So 32.2 or a G, pound mass is one slug, okay. So we should always use a rho, either kilogram per meter cubed or slugs per feet cubed. Then the three organized velocity components are U, V, W. This is the group velocity or the time average velocity of a collection of particles in the x direction, y direction, z direction. Then we said the pressure. Can somebody tell me what is the direction in which a pressure will act on a surface, either this surface or my skin or this one? Which way will it be acting? Okay. Normal to it. It's always normal. You could think of it as a collision of the molecules against the surface, rate of change of momentum exerting a force on the surface. So it's going to have a units of a force per unit area, Newton per meter squared, or pound force per square foot. Okay, so that's what it's going to have, okay, as the units, all right? Then finally, we talked about internal energy. Can somebody tell me what we mean by internal energy? What is an internal energy caused by? Kinetic energy is organized motion, okay, U squared plus V squared over 2. What would be the internal energy?
Potential energy of the molecules.
Potential energy would be like a change in the height of the molecule, gravity doing work, right? So we normally use the word potential for some force, you're resisting it, and like an electrical force, magnetic force, or a gravitational force. Another form of energy, Monday we talked about, anyone remember? Random motion. So we call that an internal energy. Okay. So more clearly, specific internal energy. So for a diatomic molecules, we said this energy is present in 5 different ways. Okay, 3 linear motion. Okay, it can go this way, randomly, or it can go this way. That's what I'm doing when my boss calls me to talk to me, about my behavior in the classroom. You can also, molecule can go up and down. Okay, so that's 3 linear motion, but they can rotate. For example, in the plane of this paper, that's a 1 degree of rotation. So this is the axis is coming towards you. These molecules can also rotate about this vertical axis. They can come out of the plane of the paper and go into the plane of a paper. So it can spin like this. Okay, that's the 2nd degree of motion. But the 3rd degree of motion is not very, very significant. Do you know why? What did we say? What happens to this degree of freedom? What do you think is happening?
Rotating along the bond?
The moment of inertia is very small because all the mass is right at the center. So in fact, it's almost zero, okay, if all the mass is right there. It's just like a ballerina, when they stretch their hand, moment of inertia increases, then they spin slowly, angular momentum. When they pull their hand in, they spin faster. I used to demonstrate it, but I used to trip over my shoelaces, so we'll stop there. So this is angular momentum is dependent on how far the mass is away from the radius of gyration or the center of the gyration. So in this case, because molecules are concentrated here, atoms are concentrated here and here, this has got a very, very low amount of energy, internal energy, so we neglect it. So we have 3 random motion, linear motion, 2 rotational motion, so we have 5 motions that produce the internal energy. Then we said the internal energy is a function of temperature. So at a low room temperature like this, it's a linear function of temperature. Delta E equal to some constant CV times delta T, okay? And we define absolute energy, no energy at all, is absolute zero. So when we say 0 degree Rankine or 0 degree Kelvin, we are talking about absolutely no energy whatsoever. Okay, molecules come to a complete rest. So as you increase the temperature, what would happen to the diatomic molecules? What other things can go wrong? Let's say you go to hypersonic flow, the temperature gets very hot, okay? Because as the flow slows down across a shock wave. What did we say happens in our last lecture? Does anybody remember? Someone from this side of the room? Could somebody tell me, please? What happens to the... Yes, sir.
The bond breaks down and becomes a plasma.
Okay, great. Before the bond breaks down, this atom and this atom are kind of connected to each other by an electronic bond. Electrons being attracted to the protons in the other one. So they start vibrating. So vibratory motion occurs initially. If you keep heating it, dissociation occurs. Then what's the next thing can happen? Ionization. So electrons get stripped off the surface. Then you have a positive ion, H plus, and a E minus floating about. Okay, we call that a plasma. By the way, plasma absorbs atmospherically the electromagnetic waves. So that's why when the space shuttle is re-entering the Earth, or a probe is re-entering the Earth's atmosphere, initially you lose communication with it. After that, the temperature cools down, the electrons snap back into place, atoms attach, become diatomic atoms. Then you start hearing the Apollo 13 astronauts saying, Houston, we are able to hear you. Okay, so that's what happens. Okay, all right. So Tom Hanks' voice comes loud and clear. Okay, so these are the important concepts that we talked about. Then at high pressure, E can also be a function of temperature and pressure, because the high pressure may keep it from dissociating. So all kind of models have been developed. They were first developed in the 60s for the missile ICBM era of inventions, then improved in the 80s for the purpose of space shuttle. Okay, they wanted to have a human glider. Imagine you go all the way up, go around the Earth, and then totally no power, no engine, you're gliding down to Earth and precisely landing where you are. It's an engineering masterpiece. No accident can happen, nothing bad can happen. Although a couple of times it happened. So they had to understand the behavior of the flow around it. So that's what they worked on it. Okay, so these are the things that we covered. So today I'm going to, going back to the module, review the airfoil concept, even though we have where's the module? We have, yesterday, on Monday, we did the intro to our course. We covered the properties of fluids. This is just a basic undergraduate. Have you all seen Navier-Stokes equations? In mechanical engineers as well as aerospace engineers would have seen it in some form, right? Yes, sir.
Formula for Knudson's number L over lambda, not lambda over L.
Okay, it should be lambda over L. Yes, last time I wrote it wrong, in the whiteboard. Okay, it's lambda over L. In the slides, it's correctly given.
Okay.
Yeah, thank you very much for pointing that out. All right. So we already covered this. So Navier-Stokes, I will not derive it, but it's there. So after we cover the aerofoil nomenclature so that you get going on the first assignment, next Wednesday, Monday is a holiday, I'll pick up here and then, we will do some stuff there. Okay, so that's a process. So I'm skipping some of the stuff here, and then I'm coming here to intro to airfoil. X-foil, you are supposed to learn on your own. How many of you have a Mac? Anybody has a Mac only? Okay. Then you have to go to the cloud computing. Do you know how to go to cloud? Georgetech.edu. Then open a virtual PC. and put your X file there. I recommend you go to your OneDrive or your thumb drive rather than putting it on their machine, because when you log out, everything goes away. Okay, so if you forgot to save that drag polar, then you lost everything. So those of you who are using the cloud computer, save everything on your local drive, OneDrive, or on a USB stick, or whichever way you want to do it. What? Or the C drive of your or the Mac drive where you did all these things. Okay. If you have trouble accessing cloud, let me know, and I'll be happy to see what's going on. Okay. All right. So let's just quickly review the airfoil part of it. Then I have some videos here on how to run Xfile, and then you'll get going on the assignment. Then I will do the nomenclature. What do we mean by 0010, 0012, 23012? So we will quickly recap it. Then we'll move on to the new stuff. Okay. All right. Okay, so we started on this already last lecture. It'll ask me all kind of questions. It won't let me default it, so that's okay, because it's not my computer. Okay, all right. No, I don't want to pay. Anybody has a credit card? Okay, already. Okay, already. So we had started on this, then I couldn't complete it because of the time. But just so quickly, we said it's used in all kind of applications. And we said early people were using thin fabric-like material. It comes from the wind sail type of experience. People knew if you had a sail, it can also be not only be used for drag purposes, it can even actually propel you. Okay, so when the wind hits it at the right angle, it'll produce a propulsive force. Okay, so you can use the wind to keep moving. Okay. So people who are using paraglider type of people, they were building a glider like aircraft, strung everything together. They knew flapping was humanly impossible for large aspect ratio things. They just tried to glide. Okay, so a lot of people tried that. But these airfoils, right near the leading edge, if you have a very, very sharp leading edge, as the flow went over there, you had a high pressure here, low pressure here, high pressure right here. So within a very short distance, the pressure was going very, 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 very adverse. Okay. So remember, adverse pressure gradient slows down the flow. It can even reverse it. So some of these airfoils, within 2 or 3 degree angle of attack, they started stalling. Okay, so they will stall uncontrollably, right? One left side may stall one way, right side may stall the other way, because when they manufactured it, nothing perfect, nothing is symmetric. There may be gusts, winds, things like that are changing. So they were crashing a lot. Wright brothers found if you could make the leading edge a little bit more rounded, bigger radius of curvature, more blunt, then the adverse pressure gradient is somewhat reduced. It was still there, but it was not as bad. So adverse pressure gradient, just as it can cause transition to turbulence, it can also cause reverse flow. So some of the airfoils, especially the short-nose airfoils, they were flow went around there, then it started stalling. There's a video on stall in my Canvas site that shows you the stall process, pictures and so forth. Okay. So they found if I can make the leading edge a little bit blunt, then I can produce a few degrees of up and down. Then I can still stay without stalling. They didn't have aileron and stuff, modern control devices that we have. So they had to physically warp the wing, For example, if they twist it this way so that the nose comes down, they were reducing the angle of attack, the question you asked. Okay? So then that side will produce less lift. At the same time, you will twist this one up, this produce more lift, then that produce this rolling moment. Okay? So they will have a rolling moment and try to control, turn, and then try to land. These type of things were being done. Okay? Then this is not structurally strong, so they had a biplane wing strung about with all kind of wires and rods and so forth. And all of those things were draggy. I mentioned to you that a circular cylinder has got 100 times the drag. By the way, the CD we are going to define, this is like 1, whereas an aerofoil that you're going to be solving is going to be 0.01, 100 times smaller. So if you had streamlined those wires, you would have gotten a lot less drag. Or if you completely get rid of a biplane and go to a single wing, and internally brace it with structural elements, then you have a very rigid wing, still flexible, but a strong wing compared to the fabric. But you don't need to externally brace it; it's internally braced. Okay. Except nowadays, they're talking about ultra-large aspect ratio aircraft, so they had to have something to attach it to the fuselage, so they're using some kind of attachment. Okay, so what goes around comes back a few years later. We will find the very large aspect ratio wings have a low induced drag, therefore they are very, very efficient. Okay, and we will define a concept called induced drag in that concept. Anyway, so this is how things were evolving. And they said, I'm going to define the aerofoil by some straight line that joins the nose to the back end. This was my drawing, my granddaughter, 7-year-old, can do better aerofoils than I do, but this is the best I could do because I have a PhD from Georgia Tech, okay, so this is my artwork, okay. So this straight dotted line is called the chord line. So when we talk about chord length, later on we will use the symbol C for chord length. We are talking about that distance, nose to the trailing edge. Now, if the airfoil is asymmetric, that means the upper surface has got a different shape than the lower surface, then we say it's got a camber. Okay. So the 3 airfoils you are going to look at would not have camber, but the others would. So this green line defines the camber line shape. It could be a bunch of numbers, it could be a semi-analytical equation, depending on how they evolve. Then you add a thickness normal to this green line, equally above and below. So you join it, thickness, then you get an airfoil. So an airfoil is defined by the chord line, which is the chord length, a camber, then thickness. These are 3 things are there. The last 2 digits of the airfoils you're looking at, 12 means 12% thick. That means that top to bottom maximum thickness is 12% of the chord. That's what it means. Okay, 12%. All right. Now, another definition is, I know you know all of these things. I'm just putting the same foundation for the entire class. So when you're flying in a wind tunnel coordinate system, the angle between the velocity of the air, we call it a free stream velocity, infinitely far away. Why infinitely far away? Because near the airfoil it starts turning around, so we cannot look at which way it's flowing. So very far away, which way it's going, air is coming. So we put an infinity as a subscript to say it's a free stream. That means uninterrupted by the presence of the body, unaffected by the presence of the aircraft. So that's V infinity. So the angle between that and this one is called the alpha. For an aircraft wing, alpha will be changing. Near the root, it will be pointing towards the sky. Near the tip, it will be pointing towards the ground. They will have a twisted wing. We will see the reason for it, again to reduce the induced drag. Okay, we will see that later. But right now, this is the alpha, is the angle of attack. The aircraft can have a positive or negative, depending on whether the nose is pointing upwards relative to the free stream or downwards relative to the free stream. Now, the pressure distribution over the airfoil produces a lift per foot of span or per meter of span, depending on the units. So if you take a 1 meter slice of the wing section, Newton per meter, we call it a L with a prime because it's a 2-dimensional lift, not a 3-dimensional lift. For a complete wing, we will just use the symbol L without the prime. That's just a convention people have used. So when we say L prime, we are talking about the lift force per unit length, Newton per meter or pound force per foot. Okay, that's the L prime. In the stream direction, you have a drag force that's caused by pressure differences between the front and the back. If you have a high pressure here, low pressure here, you're going to get a pressure drag. On top of it, you're going to get the boundary layer, something called the skin friction drag. It's the friction of the molecules as they glide past your surface. Laminar flow will have a low skin friction drag. Turbulent flow will have a high skin friction drag. Anyways, they cause this D prime pushing you backward. So airplane's job is to produce a certain amount of lift for a certain given payload, which would be passengers, cargo, fuel, everything together, gross weight, structure. But because the airfoil also is producing a drag, you need a propulsive force to move forward. In the case of a glider, gravity is your propulsive force. You are trying to slowly descending. Hopefully, along the way, you will catch I have some music playing in my radio. It's more beautiful than my lecture, but let's put it away, okay? So this is the force, okay? So this is a dimensional force. So people said, let me non-dimensionalize it this way. Then it's called a CL and CD. So this is what we are plotting in our homework number 1. Again, the lowercase L, lowercase d is reserved for 2D problems, airfoils. Uppercase L and uppercase D is reserved for the 3D wing or a 3D complete aircraft. Okay, that's again a numbering convention we universally use. Okay, all of us normally use. So the question is, again, uppercase L and D, full 3D wing or a 3D aircraft. Lowercase L and D, and then L prime D prime means a section of a wing, which is just an aerofoil section. So we said the pressure forces act on the surface. So if you have a lower pressure relatively compared to the high pressure on the bottom, that produces a lift, and the pressure force is acting normal to it. The length of the vector here is the magnitude of the pressure force. Okay? So right near the leading edge, you get a high pressure because all the kinetic energy is converted into pressure using something called the Bernoulli equation. Okay, Bernoulli equation says pressure energy plus kinetic energy is a constant for invisible flow. So right here you get a very, very high pressure. Then the flow, some of the flow turns this way. That's why the pressure starts dropping. But unfortunately, right here the pressure may start rising, which may cause stall to occur if it rises too quickly, or definitely cause turbulence to occur if it occurs rapidly. Okay. So the different aerofoils, they are shaped so that the pressure gradient on the upper surface is controlled. That's what it does. Okay. Now, Bernoulli equation says pressure is related to velocity, P plus 1/2 rho V squared. Pressure energy plus kinetic energy is a constant. Now, people say, let me subtract off atmospheric pressure, then that's called the gauge pressure. We already use the gauge pressure in our terminology, for example, in automotive car. When it says 32 psi, it's a 32 pounds per square inch over and above atmospheric pressure. That means outside the tire, you have an atmospheric pressure. Inside the tire, you have a 32 psi plus atmospheric pressure. So we take out the atmospheric pressure. So this is called the gauge pressure. Now, some of the vectors will be pointing towards it, meaning P is greater than P infinity, positive gauge pressure. Other places it will be pointing away from the surface because P is less than P infinity, the gauge pressure is negative. So gauge pressure can be positive or negative. Okay, so we are going to draw this way, but relatively again, we have a more negative gauge pressure that pulls the airfoil by the scruff of its neck. That's what produces the lift relative to the bottom. Okay. All right. Now this is a dimensional quantity. So if you divide it by, if you integrate it, by the way, from left to right, in the x direction, from the leading edge to the trailing edge, all along the lower surface, that pushes the air up. All along the top, it pushes the airfoil down. The difference is what is producing the lift. So I can group these two things together. Now, I can subtract out from each one of these the atmospheric pressure. Now, this is a dimensional quantity, Newton per meter. This is Newton per meter squared. Here you have a meter, so the units are consistent. Okay. But we can non-dimensionalize it by 1/2 rho V infinity squared C. Then this gauge pressure is divided by 1/2 rho infinity squared. That's what we call the CP, pressure coefficient. On the lower side, upper side, then we bring down the chord inside the x to make it a non-dimensional number. So X foil is literally computing this and then numerically integrating over the airfoil. Later on, when we go to the panel method, I'll show you my own panel code, show you how we integrate it. You'll see how it is put together. Nothing magical, just a trapezoidal rule, panel by panel, section by section, you integrate it. But coming back here, basically the CL is CP dx over C. So now you have two airfoils, right? One is a NACA 0012, other one is NACA, let's say 23O12. So let's see what happens, the difference between the two airfoils. So I'm going to go and see if I can find a X foil here. It's not here, let me download it. It'll complain whenever you download a zip file, usually. But I got used to my bad ways of infecting computers, so it didn't complain about it. You have already done all of these things, so I'm going to just show you an example of pressure distribution on an airfoil. So I'm going to use a different airfoil than what you all have used, 0015. All these commands would be available to you, in my video tutorial, okay? And I'm going to go to the operate. I'm going to go to the viscous operation. I'm going to use a 1 million. Then I'm going to increase my iteration to 500 times, increase the number of iterations. So let me run it at CL equal to 0.5. So you're going to get a plot like this. Can you all see this plot, okay, from back there? Okay. Can you visually see it? Okay, all right. So this is nothing more than the CP versus X over C plot. The area inside the curve is the lift, okay? That's what the CL is. Now the CD is a drag coefficient, which is part of it is caused by the pressure drag, high pressure in the front, relatively low pressure at the back will push it backwards, so you get some pressure drag, but you also get a viscous drag, okay? There's a viscous drag. So now, where do you think is the favorable pressure gradient? Favorable pressure gradient is when the pressure is dropping. So from here, which is the stagnation point, all the way up to the top of the curve is a very favorable pressure gradient. Boundary layer loves it because you have a high pressure in the back, low pressure in the front, you're going this way. It's like the first 2 weeks of this class, the professor is making a lot of jokes until you get your homework number 1 back. Then, enough of this kidding around, so we go to the Jeremiah mode, where I start giving you lectures about fire and brimstone, or at least about quiz 1 and quiz 2, okay? So that's what we would do. So over there, it becomes a turbulent immediately. You remember the curve turns around, so the pressure starts rising. It's an adverse pressure gradient. Did you see a little glitch in the yellow curve? The yellow curve is the viscous, dotted is the inviscid. That glitch is where the flow became laminar to turbulent. But it's kind of hard to visualize it. By the way, watch the yellow over D, 63. Okay? So if you go to the other window here, behind it, it shows you where did the transition occur on the upper surface. It occurred around 0.26, 26% of the chord. So that's what happened. On the lower surface, most of the flow is laminar up to 92%. Okay. So let me compare this with a 5-digit aerofoil, for example. So this aerofoil is NACA 0015. So let me go to NACA 20015. It won't operate in condition, it does not know what it is, so I have to go back to the X foil. Okay, he didn't like it. Okay, now it's 15% thick aerofoil. It's got a small amount of camber. I was trying to avoid camber, but it didn't let me do it. But anyway, this is the airfoil. So again, now go to the operating mode. Still in the viscous mode, it remembers everything that you did. Reynolds number, if you specify the Mach number. But I have changed the airfoil, so I'm going to look at the C, L over D to see what happened, and I'm going to look at the CP to see what happens. Okay. So now let's run the CL equal to 0.5 all over again. Now, when you look at it in here, did you see that now L over D has changed here, and it's not quite converged yet here. If it's 10 to the power of minus 4, let's run some more. You can put an exclamation mark and run some more. Exclamation mark some more. So make sure it sufficiently converts to 10 to the power minus 5 or 10 to the power minus 6 if you can. Now look at L over D. So this aerofoil is not so good. Okay. Why is that? Because even though it has some camber, same thickness, the transition occurred a little bit sooner. Right, 0.2441 compared to the other one, 0.26. So for the same lift, CL, my CD was slightly higher. So instead of a 63, I got a 61. So we can start comparing the airfoils, but also look at the pressure distribution, and you can look at the transition. That's why in my assignment, I asked you to document the transition location, and then look at the pressure distribution and see what happens. Okay, these are some of the things we could do. All right. So now let me see if I have one of my aerofoils stored somewhere here. Okay. I only have in Excel format, not in data format. So that's okay. We will do it some other time in the future. So when you do the assignment, start doing it. So CP, CL is the area under the curve. CD is the drag. So that far we have defined it in here. Okay, CL. Now, the reason we are doing abstract number, non-dimensional numbers than the dimensional number is because you can scale the aerofoils. You already know dimensional quantities are specific to a particular dimension. If you build a model of a Boeing 747, it may produce a few pounds. Real aircraft may produce thousands of pounds, hundreds of thousands of pounds of a lift. But if I scale it, they will have the same CL, same CL. So Wright brothers realized this. That's why they were making models of it and testing it. Some of the other people, they didn't know you could make a model and test it. They were building the full-scale article, which was very expensive, and they were running off the bridge or running downhill and see what happens, which is very expensive proposition given today's medical coverage costs. Okay, they had models, so scaling is important. But when you scale it, you have to match the alpha, otherwise you'll get a wrong answer. You have to match the Mach number, and then you have to match the Reynolds number. Okay, Reynolds number. Have you all seen Reynolds number before in your mechanical engineering and aerospace engineering life before? Okay, it's on a numerator you have all the inertial effects of the molecules moving, causing change in the velocity, but also changing the pressure, therefore producing forces. That's the inertial forces. The bottom side is the viscous forces, so the ratio between them. So when the inertial forces are dominant compared to the viscous forces, you get a high Reynolds number and vice versa. Okay. Anyways, so you're familiar with all of these. Now, models are good. That's why if you look at NACA data, not NACA data, this is NACA data here, and then the Virginia Tech data, they didn't match the Reynolds number because the tunnel conditions were different. Okay. More or less the CL versus alpha matched quite well until the curve turns over, which is called the stall. Okay, when the upper surface flow excessively separated, you no longer produce the lift that you want to achieve, then you get a stall. So other than the stall behavior, these two data taken almost 60, 70 years apart from each other match very, very well. Even though totally different technology, totally different scale, totally different things. Okay, so that's why we non-dimensionalize things. So by the way, the curve will have a slope of 2 pi. We will see in our aerofoil theory. I will not go over the details of it, but because it's undergraduate material, but in incompressible flow, it will have a slope of 2 pi. And where it crosses the x-axis is called a zero lift angle of attack or angle of zero lift. So it's sometimes given a symbol alpha naught. And what happens when you camber the airfoil, you're basically shifting the curve up or down. That's what we are doing in here. Okay, so that's what we are doing in here. All right. So in incompressible flow, in inviscid theory, will give us this kind of a curve fit. And the drag is caused by skin friction and by pressure. At high Mach number, later on in our course, by week number 5, we'll start talking about wave drag. So the skin friction is because as the flow slides past the body, molecules want to move, body wants to stay put, so the body pulls the molecules back towards it, but then the molecules pull the body back. So that's why this is a drag force. So aerofoil is dragged back, and you have to overcome it by providing the propulsive force. So in a laminar flow, laminar comes from the word laminate, layer by layer. Each layer of fluid is going by itself. They do mix with each other by molecular diffusion. Okay, so one molecule from the bottom may migrate to the top, and another molecule go from top to the bottom. It's like a freshman sometimes in your junior class, because they have done all the AP classes, nerds, raising their hand. Every question professor asks, you want to hit them on their head. So they are there. All the rest of you are juniors, and then you are migrating diffusion. Likewise, occasionally a senior who has transfer, didn't take the intro to AE, they will be in the intro class, right? So this is a molecular thingy. So in a cup of coffee, I used to demonstrate it. If I have sugar at the bottom, coffee on the top, it tastes bitter. But after a while, the molecular diffusion, it mixes. Then when I drink it, it's sweet at the end of the lecture. Okay? You are happy because I finished talking. I am happy because the coffee is sweet. Okay? So that's a laminar mixing. So air can layer by layer be traveling. The only way they mix with each other may be by molecular motion. That's why this molecule is slow here. How did this molecule know there's a wall here? Because a zero velocity, nearly zero velocity molecule migrated here and mixed with it. Same way, high velocity molecule migrate here, giving it this forward force. Okay, so that's why this mixing takes place. Turbulent flow is like taking a spoon and stirring it up. So you have eddies. Think of it as a giant earth movers taking a scoop of sugar and putting it to the top of the cup, and taking a bitter coffee and pushing it to the bottom. So mixing takes place in turbulent flow, not only in 2D like this, but also in 3 dimensions. It's totally chaotic, totally disorganized. There are only 2 people who know how turbulent flow behaves. One is God. The second one is Dr. P.K. Young, who teaches the turbulent flow. He does a direct numerical simulation of turbulence. He's a walking encyclopedia. I hope you'll get to take his class. He's a wonderful teacher, very fundamentally focused on these type of things. And on the other hand, if you average it, take thousands of samples, average it. This is what Reynolds did. The same Reynolds with the Reynolds number is credited with. When he did that, you look like an organized motion like the laminar flow we saw earlier, except now the flow is well mixed. Okay, well mixed means what? The high velocity has been brought close to the surface because of the eddies mixing together, and the low velocity also has penetrated up there. So the boundary layer is thicker, but a higher velocity flow is scraping past the surface because it's been brought close to the surface. That's why the turbulent flow has got a higher skin friction drag. Okay, that's what happens. So if you look at on the wall, you get this shear stress tangent to the surface. You can divide it in the direction of the flow, in perpendicular direction of flow. So if you integrate it on the upper and lower surface, you'll get the skin friction drag. So here, for example, it talks about the skin friction drag. This is the pressure drag. Okay, it gives you both information in X-file. So skin friction drag is caused by the layer of fluid sliding past the surface, and that sliding past the surface occurs because of the high velocity flow being brought close to the surface. So in X-file, it computes the skin friction on the upper surface, lower surface at different points empirically, using some method called Thwaites method in the laminar region, Hertz method in the turbulent region. Normally we are covering those in the viscous flow classes. I love to teach those type of stuff, but we will be stuck there in the viscous world. So I have to kind of tell you, these can be computed empirically in the blink of an eye, right? X-file does it. So you get the answers. Then you plot the CD. Okay. By the way, you can also do a CL versus CD in X-file by giving a sequence of CL and CD. You all know how to do that, right? If you, for example, if you say C sequence -5 to +5, the question that was asked by you in steps of 0.1, then it'll do all the alphas as quickly as it can. Then it's done. Then if you look at the plot here, it's got some values here. Notice that it's producing garbage values. Okay, that means it did not converge at all. Okay, because the errors are way too high. So you may need to increase the number of iterations that you are doing. But for the 3 examples I have given you, you should get well-converged solutions. Has anybody tried the assignment yet for any aerofoil yet? Did it converge okay for you? Okay, already. On the other hand, anytime you do a live demonstration, things always go wrong. Normally, we will go to a commercial if it's a TV station to fix it, but here there are no commercials. I am the comedian, and I'm the one, okay, going to be doing this one. All right. So this problem occurs because of it's not sufficiently converged, but anyway, let's move on. Okay. So it should produce a bunch of values, but you can also dump it to a file. There's a commands for dumping it, CLCD, then you can copy it to a X-file, Excel, plot it. Okay, all right. So skin friction can be empirically computed. So this is what this assignment is. Most of the things are all about. Now, one more thing. We talked about the nomenclatures of the airfoil. So let's go to the module section. Naming convention. So what does the 0010 mean, 0012 mean? So there's a public domain website here where all of these things are available, okay, to you. Okay. If you wanted to know the exact website where I stole this from or got this from, if you click on this arrow here, it'll take you to that particular website. Okay, it's a Wikipedia. You know it's a Wikipedia because it'll ask you to make a $20 donation, every time you click on it because you've been using it so much, okay? But let's look at the 4-digit airfoil. This was one of the first things that they did. So they had just a 4 digits to represent it. So the first digit told the percentage of the camber, okay, that's what it was, okay? Then the second digit said where does the maximum camber occurs. The last 2 digits are the thickness. For example, when we say 2412, 2 stands for a 2% camber. It's occurring at 40% of the chord line, maximum camber. The airfoil itself is 12% thick. You don't need to memorize it. It's an open book, closed book exam. But when you're in an industry setting, your design boss may ask you, should we go with 0015 or 0012? You can't be flipping through my notes or things. You need to kind of know at least some of these numbers, okay? But the more you use it, the more familiar you will get it. And so 4-digit airfoils were one of the first things that they did. For example, 0015, 0 camber, so you don't need to say where it is maximum camber. Then 15 is the 15% thickness. Okay? So this is the 4 digits were developed first. Then, after a while, people started developing 5-digit airfoils, next generation of airfoils. So, the first, they had a form LPSTT. L is the first digit, P, second digit, and so forth. L is the optimal lift coefficient. For example, 23/12, 2 is the optimum, 0.2 is the optimum lift coefficient. Okay. To a 0.15 times 2, so 0.3 is the optimum lift coefficient. So the first digit, you multiply by 0.15. Then the P talks about where is the maximum camber occurring. So for example, if you use the number, it's 0.05 times P. So for example, if you use number 3, 3 times 0.05 is 15% of the chord. Okay. Then 1 says whether it's a reflex. That means reflex means inflection, convex followed by concave camber. No reflex means 0. So 23 O means that camber line has got either positive curvature or negative curvature. Curvature does not change. Okay. So this is how they were numbering it. They'd have some kind of a nomenclature, just like a Sears catalog or your Amazon catalog will have a catalog number. They had to number them, but they wanted to have a some rationale behind it. So this is how things were evolving, and eventually 6-digit aerofoils were developed. So there is a report here in our Canvas site called Abbott and Deinhoff. I'll just take 5 more minutes, then we will quit. Which has got tables of thousands of aerofoils that have been generated, and also plots of thousands of aerofoils. So I'm going to download it. And I'm going to go to the folder and open it with using Adobe Acrobat. It'll again ask me, do you want to make it default? Let's see what happens. Okay, maybe not. Okay, so this has got thousands of aerofoils. A lot of it was done in the 1940 time frame. Okay, so most of them at the Langley Tunnel. So I'm going to go quickly to some plots towards the later part of it. Okay. Are you all able to see this okay, or shall I make it bigger, a little bit bigger? This is, somebody asked, should a CL be x-axis, CD, y-axis? So, in this graph, the convention is the x-axis is CL, the y-axis is the CD. So that's the convention we will use. Okay. So each of these graphs is for one specific aerofoil. For example, this is a NACA 4. Four, 18% thick aerofoil. We see multiple curves here, CL versus CD. For some of them, the difference is because the Reynolds number is changing. Okay, so the higher the Reynolds number, the lower the CD roughly, because of the way things get non-dimensionalized. But if you make the surface rough, sandpaper, things like that, then it'll become the drag will shoot up because it'll become turbulent way too soon. Then you get a higher drag. Okay, so the topmost curve here is a very, very rough aerofoil. The bottom curves are smooth aerofoils of different Reynolds number. Right? The left side is just the CL versus angle of attack. This is the pitching moment versus angle of attack. So this is the alpha, pitching moment, lift. Again, for different families of curves. Notice that the roughness did not affect the CL, but it dramatically affected the CD. Okay? So people realized this, but old days they were using fabric. Then, just coat it with the paint. Fabric can be very rough, right? Like even my jeans or my thing. So today we use a polished, either a plastic, composite skin or a metal skin. Okay, that's what we use. Also, the rivets were sticking out. They were roughness elements, right? So when the old generation aircraft, if you look outside, you'll have rivets, just that's how they manufactured them. During the Second World War, Ford plant in Marietta, which was making cars, were converted quickly into an aircraft factory. That's how the Lockheed Georgia came about. So they hired the same workers who used to be making cars, gave them each one a rivet gun, and they said, now you're going to be making airplane. Welcome to the Second World War, folks. You are now war fighters. Okay, so they would be doing lots of rivets sticking out, producing a lot of drag. Okay, now we have an ultra smooth, fiberglass type of thing. So this is what's happening. So let me go to a 5-digit aerofoil drag polar and see what we get. Okay, so this is a 5-digit aerofoil. Let's see what aerofoil this is. No, it's actually a 6-digit aerofoil. 1, 2, 3, 4, 5, 6. Okay, the last 2 digits is usually the thickness, but different numbers have different things. But do you see this bucket-like shape here? That's called a laminar drag bucket. Okay, laminar drag bucket. Because in this region, the flow is dramatically low, the CD is dramatically low, 0.004, because the flow is laminar. So over most of the upper surface or the most of the lower surface, the flow is almost laminar. Laminar flow has got a less drag. Of course, at a high lift coefficients, the boundary layer will become turbulent, so it takes on the parabola-like shape that we talked about earlier on. Okay, so technology evolved. People learned to design laminar aerofoils, and that's what happened here. So, lots of information, on these things. And all of this is free of Uncle Sam, available to you. So, in the 1940s, people depended on NACA to give them the aerofoil shape. But by 1960s, Boeing, McDonnell Douglas, Lockheed had their own tunnels. They said, we're going to develop our own custom aerofoil. We're going to use it on our aircraft. We're not necessarily going to share it with anybody else. So that's how it evolved. Okay? All right. So we are close to 9:15, so I'm going to stop here. Now you should have everything you need for your homework, right? So you should be able to do your homework. You can still ask me questions. Please ask me on Teams. And watch the video. And then Monday, no classes. Wednesday, we will meet. And now we will move on to the new topics, streamline, vorticity, other type of topics. All right? Thank you all. Have a great weekend.